Hello, this is Jack Jackson. In this video we're going to be talking about flow curves of vector fields. So if we can take a vector field and parameterize it in terms of a parameter, say t, then we have x and y both as functions of t, and then our vector field, which of course is a function of x and y, then is rewritten as a function of t. Furthermore, if we think of t as time, then we can think of this vector field as a velocity vector field. The vectors are velocity vectors. The position vector is then x of t comma y of t, or x of ti plus y of tj. It's then an antiderivative of the given velocity function, v of t, also known as r prime of t, or our original f of xy, rewritten in terms of t. So we can think of taking a specific particle, or at any point in the domain, we could drop that particle into the field, and the velocity vectors show us which direction it's going and at what speed. And so that particle will then trace out a path as it goes into motion. The path that it traces out is a curve that's known as a flow line. I'm going to call them flow curves because they're typically not lines, okay? But they're probably more commonly called flow lines, sometimes also called streamlines or integral curves, so multiple names for the same thing. So different choices for initial position on the curve yield different specific flow curves, okay, and with specific position functions. And if you think about it, that's because you're given this function here, this f to begin with, which in other words you're given v, or r prime. You want to reconstruct r, you would have to do an antiderivative that's going to have the plus c, which is a plus constant vector in this case. And that's going to basically pick a particular initial point, and that gives you a different curve. The family of all these different flow lines or flow curves is called the flow of the vector field. We can graph several of these together, but just like when we're graphing the vectors, we can't graph every single vector because there are infinitely many of them. We can't graph every single flow curve, but we can graph a representative set of vectors and a representative set of flow curves. And what we should see is then that the velocity vectors, that is the original vector field f, are always going to be tangent to those flow curves. If you start it with the tip or the tail on the curve itself, then the tangent vector will be the original, or the original vector field will be a tangent vector at that point. And we'll have those all the way along. Now these things show up a lot in lots of real-world settings. Here's an example of a set of flow curves from NASA, and these are flow curves of surface currents in a portion of the ocean, and you can see those put together here by NASA based on certain data that they have collected. So basically, what this is saying, these are the flows of the current. So if it would stay like this for a period of time, you could drop in an object here at the surface of the ocean, and it would flow. That object would flow along one of these curves. Okay. And there are lots of other applications, but that's just an example. So let's take a look at a specific example here, a little bit simpler example than say the flow curves in the ocean there. So we're going to determine the flow curve where for a given vector field, 1, 4x is our original function. Remember, that is a vector field. So all the vectors in this vector field are going to the right one, but the amount that they go up or down depends on what x is. We're going to start with a point at -2, 6 at time t equals 0, and we're going to see where that point would move as it goes through time, or where that where that particle would move. Now, according to this, we need a parameterization for x, y for the position function to trace out the flow curve. And what we know is that the derivative of the x component of the position curve with respect to time is going to be the x component of our given field. So x prime of t is 1, and y prime of t has to be 4 x of t. So here's how we solve this. We know that if x prime of t is 1, when we do an antiderivative, we know we get t plus a. So this is you want to think of this as a function of t. Okay. So it's t plus a, where a is some real number constant. Now y prime of t is 4 times the x. So substituting in, y prime of t is 4 times parentheses t plus a, which distribute the 4. Y prime of t is 4t plus 4a. Now we do an antiderivative there. And of course our whole family of these. We get, let's see, the power goes up to t squared divided by 2, so this is 2t squared. That 4a is a constant. It picks up a factor of t. And then we have our plus constant at the end, which I'm going to call the constant b this time. A and b are constants, but they're real numbers. So our position function is t plus a, comma, 2t squared plus 4at plus b for various values of a and b. So plugging in a and b, we get that. Actually, a and b are the initial points at time 0, because if you see that r of 0 is, well, it's ab. So we can start at any particular point we want. Now we decided to start at the point negative 2, 6. So AB was negative 2, 6. So with those specific values for A and B, we plug in here. And we get R of T is, plug those in there. And we get that. Okay. And this is a parabola. One way we can see that is if x is t minus 2, then t is x plus 2. So I can put the x plus 2 in place here, and that's going to be y in terms of x. Square this out, combine like terms. I'll let you work the algebra out yourself, but it turns out to be 2 x squared and then minus 2 is a parabola. It's going to be centered up on the y-axis. The y-intercept is 0, negative 2, and sure enough, it should start up here at this point here. At negative 2, 6 at time 0, and it's tracing out in this direction. Notice that these flow curves have a direction to them. Let's see what else. We've got the velocity is the derivative of the r function, and we should check that to be sure that it works out to be this 1 comma 4x. Of course, we engineered it to be that, so it better work out. But let's just double check. If we take the derivative here, we do get 1. Derivative here is 4t plus 4a, which I can factor the 4 out. That's 4t plus a, and that's 4 times the x value up here. So that is correct. And here's the parameterization for the velocity curve here, which is our initial thing, but just rewritten in terms of t. So it's big F, but of t. And there it is. And so you can see the vector field here. Some of the vectors are plotted. And here's our curve. If we were to take any point along this curve and then look at the vectors, they would be tangent to it. So all of them here over on this side here are pointing down to the right. At the bottom here, it's pointing directly to the right. And on the up here to the right of the vertex, the vectors are pointing up and to the right. Notice they're all going to the right 1, so all the vectors are going to the right the same amount. That was an original thing. And the 4 times the x's are what the y's are going. So when x is negative, these are pointing down. When x is positive, these are pointing up. When x is 0, they're just pointing neither up nor down. They're pointing just strictly to the right one. Of course, this has been scaled back some, as most vector fields are when you graph them. So these vectors actually have a length of 1 right here. All these here along the y-axis here, and but they've been scaled back. Looks like probably by a factor of a half. Okay, let's look at another example. Let's determine the flow of this vector function f of xy is negative y comma x, or negative yi plus xj. So I use some software, I use some GeoGebra software to graph this, and we see some vectors here, and this suggests that maybe we have some circles going on here. But we know we have to have a parameterization where the x prime of t is the opposite of y, or whatever t is, as a function of t, and then y prime has to be the same as the original x function. So we're thinking about circles, we're thinking about functions whose basically you have a function and its derivative here is the opposite of the original function. Here you got some things going on here. Well, if you think sine and cosine kind of are going to work out that way. So let's take a look here. And I'm going to give you a parameterization and then prove that it works. Okay. So we know we have to have these differential equations have to be solved here. But we know the x of t, let's take it to be a cosine t and y t to be a sine t, where a is some constant. And you'll see that I'm going to show you that this is going to work. If you take x prime of t, the derivative of cosine of t is minus sine of t, but you still got the a. So x prime of t is minus a sine of t. And then if y is a sine of t, the derivative of that is a cosine of t. Well, notice that a cosine of t is exactly what I let this be for x, so that works out. And a sine of t was y, so x prime is minus y, and that does satisfy these differential equations, right? That the derivative of the x is minus y. That's what this is saying right here in the original function. And the original function, the x, is the y component, so that's going to be the derivative of my y component of my position vector. So my position vector has components a cosine of t, a sine of t. All right, so let's continue with that. The f of t, or v of t, or r prime of t are all the same thing. It's just this original function here, but rewritten in terms of the t's. And that's minus a sine t, a cosine t, which of course is minus yx like it's supposed to be. Now, if you take the original x squared plus y squared from our original parameterization here, that's a cosine of t quantity squared plus a sine of t quantity squared. That's a squared cosine squared of t plus a squared sine squared of t. Factor the a squared out. You've got cosine squared of t plus sine squared of t, which is 1. That's our basic Pythagorean relationship on our circular trigonometric functions there. So that's just 1. And so this reduces to a squared, and you've got x squared plus y squared equals a squared, which is a circle of radius a centered at the origin. So the flow curves are going to be centered at the origin, and they're going to have particles are going to flow around this thing actually in the positive direction, counterclockwise, centered at the origin. I've graphed some of them here from, say, 0 to 10. Okay, so let's take a look here at, there's the vector field there, negative yi plus xj is our vector field. There's the vectors. And here is a circle centered at the origin, so this blue one is a flow curve, regardless of where I put that starting point. So basically, picking a starting point is really kind of more or less going to be the same thing as picking an a value. Okay, And if you look at one of these vectors, if I go to the tail of one of the vectors, any one of them, you'll notice that that vector is going to be tangent to that circle. These vectors are not spaced out with equal r values, so equal radius from the origin. So these are not all going to hit on the circles when I put different circles. But if I go to any one of them, like there, you can see a tangent vector. If you go to here, you see that that's the tangent vector here. Okay. In fact, in this particular example, all of these have the same length of these vectors here. So the speed is, well, that's not true. The speed is not the same. It's getting bigger. They're getting bigger as they go further out. The angular speed turns out to be the same. Okay, so I'll show you that in just a minute. Okay, I'm actually going to go to this one here. This is the same vector field, negative yx, different thing here. Notice these vectors are getting longer as you go out, so the speed is actually getting bigger. But this one allows us to put these particles in motion, and you can see them moving around. So it's moving in a sort of a rigid pattern at the same angular speed. Okay, and so this is spinning like if you were spinning a disc of some kind, like a record or a CD or something, spinning at a constant rate. And I can actually trace these points, and you can see the paths that they're tracing out. And I think you can see that these particles are going to be tracing out in circular paths. Right, and those vectors are tangent to the curves along the paths. Okay, looks like we made it over a quarter of the way around. So if I let this run long enough, it will run around and it'll come back to where it starts in a certain amount of time and trace out a full circular path. Here's another version of more or less the same thing. This one is a little different. This one is a different field. It's the minus x minus yx, but then both terms are divided by x squared plus y squared. So here, instead of getting longer as the vector is getting longer or faster speed as we go further out to keep the angular speed the same, here they're actually getting smaller in length as they go out. So the ones in the middle are actually going around a lot faster, both in terms of just linear speed, but also in terms of angular speed as well. And so you see this, but they're still tracing out circular paths. Okay. So if you want to just see the paths there, you can see them. One thing that's interesting here is this one, you can actually put the vectors on there. So now you see the vector at each of these points. These are the vectors, these original vectors up here with those x and y coordinates, and you can see that they're always tangent to those curves, to those flow curves. Typically called flow lines, even though they're not lines. In this case, they're circles. So those flow lines or flow curves are circles here, and you can see those graphed out. Okay. So there are there's a slide with a couple pictures of those, and the slides have links to the GeoGebra activities that I just showed you. Thanks to the authors of these, I've tried to cite the authors of these GeoGebra activities. Here's another one that has a, let's go ahead and go to this one as well. And this one here is something that we have. This is actually something similar to what we had before. Here's the field minus Wx, Wy for different values of W. And here it is. I can start these points moving around. This one's moving in the counterclockwise way. If you notice, it was minus on the X, positive on the Y. And where if I switched it to the that was the clockwise direction before. This is the counterclockwise direction. This one is actually, let's see, when X is positive, it's going to the left. So the W is a positive number here. I'm sorry, when Y is positive, it's going, yeah, I think that's a typo. I think this is minus Wy and then Wx. Yeah, I'm pretty sure that's backwards. Okay. But notice when Y is positive, you're going to the left, and Y is negative, it's going to the right. Okay. Let's stop that. We can look at here's one where let's see, I'm not sure. Hopefully this is something like this. This is kind of like the second one we were looking at a while ago, or one of the ones we were looking at, where it's going a little faster in the middle. I can randomize the points like this, and you can see that that changes that coefficient in there. And you can see here that these are the vectors are bigger in the middle than on the outside, so these out on the outside are going more slowly. And then I can switch the direction. This changes the sign in our of both terms, both components of our vector field. Let's see, here's some motion near a wall. So it's coming down and then going out. It's kx and then minus ky for that one. And this is interesting here. This is an example of what we call a source. So you have a source at the origin, and things are seeming to flow kind of out away from the origin. No matter where these points are, they flow away from the origin, actually in this case in a straight line. So all these vectors point directly away from the origin. So the flow curves here would be rays that start at the origin and then go out. You know, basically lines, half lines coming out from the origin. If you reverse the direction, then things are coming into the origin, so your flow curves are rays coming into the origin. Okay, in this case, the origin is called a sink. I think we looked at all of those. Okay. All right. Yeah, I need to fix that because I think that's actually incorrect. So, okay, I think all the labelings are correct at this point. Okay, I want to look at one more example. And here's the example here. Here we're going to start with a potential function, a function of two variables. Z is a function, or Z or F is a function of X and Y. And here specifically I'm starting with f of xy is the lateral logarithm of the square root of x squared plus y squared. And I can look at the gradient function of that, which produces a vector field. X over x squared plus y squared is the derivative there of that, whether you're taking, and then y over x squared plus y squared is the derivative with respect to y. So derivative with respect to x and derivative with respect to y, of course, of this original function finds the gradient, which is a vector field. And you can see it graphed here. Okay. And if we think of that as a velocity field, actually I don't want to think of that as a velocity field, I want to think of the opposite of that as a velocity field. So I'm going to multiply both of these terms by -1, then that's the velocity field that you see graphed over here. And I will place some particles in this velocity field. And notice that we have a sink here, that they're approaching the origin. And in fact, they're approaching in straight lines. So the paths would be straight lines, the flow curves. And here are the points here. Let me show you this one oops, let's go back. Let me show you this thing in motion, which is here. And I can place the points in motion, and you can see them flowing into the origin over here on the left. Just focus your attention on the left for just a minute. And they're coming in a straight line. So if you were to follow one of these points, let's say we follow this one right here, notice it's following these vectors right along here in a straight line directly into the origin. And if you follow that point, so that point, let's put the axes on over here. So here's a point, let's see, here's one near the axis. Okay, here's one coming in up here, positive x and positive y, so that's out here. So you got one out here, for example, you can see them coming in straight toward the origin. They're just going down the drain here. You can see them continue to flow in the surface, going down, it's toward an asymptote here on the surface here. So if you look at it straight from above, if I've got to get it oriented the right way, let's see, this way. These two graphs are essentially the same. And you can see what's happening there as they're going down the drain. So it gives you an idea of what a sink looks like. Okay, so we have that. Next, let's look at one more example. This is kind of cool. Now let's look at a 3D example. So far we've done all this in terms of flow curves for a 2D vector field. We could have a 3D vector field. And so you're going to have x, y, and z components of your vector field. In this case, the I component is 10 times parentheses y minus x. J component is x times parentheses 28 minus z, close parentheses minus y. And the k component is xy minus 8 over 3 times z. And I have a couple of points here that we're placing. I can place them sort of anywhere I want. There's one in the first octant. Here's one over here. Okay, and I can start this in motion, and we can see what they're doing. Let's go ahead and trace where they're going. Okay, so we can see what kind of motion is happening here. Okay, and we can see those curves. Okay, it's not quite a motion in a plane there, you can tell. So all those points are going around there. So they're making some kind of motion. It's easier to see if you're get a better idea what's going along if we can look at multiple views here. I can add a bunch of particles, and we can see what all those particles are doing as they trace through time. Now, I don't have the vectors graphed on this one, but we do have some of the curves. So the flow curves here are, of course, two-dimensional, not two-dimensional, but three-dimensional curves in three-dimensional space. Okay. So hopefully that gives you some idea of what's going on there. Now, if we were to graph these vectors, then any one of these vectors, let's look at the red. Let's see. One of the red pieces, let's say right in here. If you take one of these points, then the velocity vector, which is given by this vector formula here, will end up being a vector. If you put the tail at that point, it'll be tangent to this curve, and it will be in the direction of the motion of the particle. There's a static slide of the same thing. All right, so hopefully that gives you some idea about what we mean by a flow curve of a vector field or a flow line, and gives you a few examples. We worked with some details worked out for two-dimensional, and then just gave you a little example of a three-dimensional version as well.